Hey there, my name's Mitch.
And my name's Tom.
And today we're doing an experiment on the driver amplifier of the X-Microwave Kit provided by Keysight. So Tom, do you want to start us off?
Yeah, so the power amplifier is not a significant component on the transceiver design, especially for the receiver. As we know, the signal, RF signal put into the receiver has a very low power level and also include some noise. So it is very important to have some very good power amplifier with very low noise figure and has a very good linearity. So there are a couple of the parameters today we want to measure. So the first is the S parameter. We know the power amplifier, it is also a two-port network, but there's a little difference between the passive components we have measured in our lab 1 and lab 2. So Mitch, would you want to let us know what is the difference?
So when looking at the difference, we mainly focus on the S parameter or the scattering matrix of the driver amplifier. And the main difference is that S12 and S21 will not be equal because the P out cannot act as the P in, and the P in must only act as the input power because it's an amplifier at the end of the day. The input signal will be amplified and the output signal will be at a much greater amplitude than the input signal, which is why S12 and S21 cannot be equal.
That's a good point. If you are messed up this point, sometimes you're probably going to burn the power amplifier. So another parameters we want to measure is of course the power, as the output power is based on our input power. But as I said, the power amplifier is the non-linear circuit, so the output power could not be always linear. At some power level of the input power, the output power for the fundamental signal would be saturated. So there's another term, it's called the IP3. So Mitch, would you want to give us the brief introduction about what is the IP3 and how it is generated?
So the IP3 is the point at which the IMD3 and the fundamental line or fundamental slope intersect. And it usually tends to have a 3 dB difference from the actual saturation point of the fundamental slope.
Yeah, so the IP3 is very important, like the point to evaluate how good the power amplifier is. But how we detect the IP3 and how we generate the IMD3, that's the important point. So Mitch, would you want to give us the tip?
So now we'll look at this diagram down here. This is the power out versus the frequency of the input. So we swept the power in, and at different power ends, we have a two-tone frequency. We also input a signal for two-tone frequency. And at certain power ends, the IMD3 peaks will show up in respect to P out at different frequencies as well, which is why you see at a greater Pn on this graph is when the IMD starts, because it doesn't exist at lesser Pn points. And that's basically how we related our P out to our P in with this graph based on when the IMD3 peak showed up.
That's definitely correct. Okay, so we have do some introduction and we know how to measure our power amplifier. So let's go switch to our test bed.
All right, let's go.
Okay, so now we are seeing like the X-Microwave test bed provided by our Keysight company, and there are a couple of the power amplifiers existing in this test bed, and we're gonna pick one of them. And this amplifier is the part number is the 805311, and it's actually working from the 30 megahertz to the 6 gigahertz. So now we're seeing that we are using the 2 SMA cable to connect the input output of the PA, which is to measure the S parameters. So after do the measurement of the S parameters, we're gonna measure our output power. So we're gonna switch this cable to connect to our signal generator instead of the PNA. So let's see how our measurement is the data is be like.
So here we have our component specifications of the ADL5611. As you can see on the presentation slide, we have the diagram of the functional block. Then now looking at the different parameters, we looked at the frequency range, the fixed gain, the OIP3 at 1900 megahertz, and the noise figure. We can see that it has a very good noise figure at around 2.4 dB and an OIP3 at about 37 dBm and a fixed gain of about 22.2. And as Hanqing mentioned earlier in the video, it operates from 30 megahertz to 6,000 megahertz. So now we'll look at the experimental testing results. Let's take a look at the S parameters. So taking a look at S21, we see that the gain, S21 signifies the gain, and it's around 22.2 dB, which is consistent with what we saw on the data sheet. And next, we'll take a look at the S11, which is the return loss, and it consistently stays under negative 10 dB over the entire bandwidth of the frequency range. And same deal for the S22 and S12 parameters. Now we'll move on to the results of the P out versus P in diagram. And as you can see, we graphed both the IMD3 and the fundamental lines. And at its intersection, we were able to find the IP3 intercept points. And for the IIP3, which concerns the input power, it was around 4 dBm. And for the output IP3, it was around 21 dBm. Having a high input power means that the amplifier is a high performance amplifier and doesn't approach saturation at low level powers. And with that, that concludes our experimental results. Now we'll move on to the latter section of our video. So Tom, how do you think our experiment went?
I think we do an amazing test. So we we got a very clear introduction, and we show our very amazing test bed, and we collect our data, which have very great agreement with our simulation and theory. So Mitch, how do you think about that?
I think driver amplifiers are very important in the applications of receivers, and I think our experiment today showed that the ADL5611 power driver amplifier is a good component to be used in a receiver circuit.
Yep, that's true. So hopefully you guys like this video, and see you guys again.
All right, signing off.